Yes. So, hello everyone. My name is Kendall. And yes, I'm going to be talking about ultra-fast pyrolysis that I've been working on for the past few months. So we focused on silicon oxycarbide ceramics. And with this pyrolysis technique, we can go from room temperature to our pyrolysis temperature in 20 seconds. I chose a time of 20 seconds, but you can go faster if you want to use extreme settings, but I just decided to stick to 20 because it was a good choice for me.
Less disruption.
Less disruption. So similar studies have been done for SIOC ceramics, but they are more on the order of several minutes of pyrolysis. So this one going in just a few seconds is pretty new. So I decided that I will just try this out with some silicon oxycarbide and see what the differences are between them, between that and standard pyrolysis. So we use two compositions. The first one is bis triethoxymethylsilane and triethoxysilane on the top, which I will abbreviate to just calling BTEM. And we have a methyl triethoxysilane on the bottom, which they're obviously pretty similar, but they do lead to different structures. So those are the two silicon oxycarbides that we tested. So for the pyrolysis methods themselves, so everything was under argon and we went to a temperature of around 1100 Celsius. So our standard pyrolysis that I'm going to call it was with a regular old tubular furnace. We chose a heating rate of 2 degrees a minute, which leads to a total ramp time of 9 hours. Whereas for fast pyrolysis, we have a 20-second ramp time. And the way that the fast pyrolysis works is we have an electrical current being sent through these two brackets, and in between the two brackets is suspended a piece of graphite felt. So we cut a little slit into the felt and we can stick our samples in there. So we can fit, I've used mostly flat samples, but you can fit a couple square centimeters at a time for each round of pyrolysis. So the major annoying thing about the fast pyrolysis is that the graphite felt does degrade over time. So you do have to replace it every few runs. And the actual settings that I have to use depends on the size of the graphite felt. So the same settings for my previous piece might be not hot enough for the next piece if I cut it a little bit bigger on accident. So I do have to go through a sort of calibration phase at the beginning of each piece of felt, and then I can continue. So I use these two pyrolysis methods and the two different compositions, and I got some samples, and then we can move on to characterization. So first one is FTIR, which unfortunately it's not very exciting for this one. So for all of these, I'll have BTEM on the left and NSF on the right. And then my standard pyrolysis is blue and my fast pyrolysis is orange. So the FTIR did not reveal any differences between the two, which was not a big surprise because they are the same composition. So there is no significant difference here with the FTIR. The next thing we did was we decided to see if there was some difference in free carbon, perhaps. So we did, we took our pyrolyzed samples and we did a TGA in air to see what the differences are. I didn't show the TGA plots because they're the same for both samples, but I did show the FTIR, which this is where we should see a difference, if there would be any difference. And again, it's pretty much the same all around. So this is the one where you see the big difference. This is silicon NMR for our samples. So there are 4 peaks that we looked at, M, D, T, and Q, which is mono, di, tri, quad, which tells you the number of oxygen attached to each silicon. So we noticed with both of our compositions that our fast pyrolyzed samples had bigger T peaks and smaller Q peaks. So what that indicates to us is that during the fast pyrolysis, our samples did not have as much time to undergo redistribution reactions. So starting off, every silicon will be a T, and then as we hit the pyrolysis temperature, redistribution reactions will occur, and then we will have moving from T to any of the other peaks. So this does indicate, this is the biggest difference between our two samples, is depending on the heating rate, you can select for which kind of silicons that you would like, if you want them to be T, Q, D, or M. So in conclusion, our biggest, the biggest difference that we noticed was for the NMR. And we can say that the redistribution reactions, they are time dependent. And depending on how much time you give the sample to do the redistribution reaction, you can select for certain properties depending on what you wish. So for the it would be interesting to see what if we decrease the time even further. What if we went to just 2 seconds or 3 seconds or 5 seconds or whatever we choose to do. For my acknowledgements, I would like to specifically thank Mattia and Imangala at the University of Trento because they helped me a lot with my project and getting everything, getting the samples prepared and getting the analyses done. So a big thank you to them.